Okay. Hi everyone, thank you for having me today. I will talk about the main results of a paper that together with Patrick, Leonardo, James from the University of Nottingham and Silke, and also Sam and Ruth from the King's College in London, and Carlo from the University of Newcastle, we put together a paper about the results of our experimental setup in superfluid helium. And so this is how the setup looks like. You have already seen it from previous presentations. What I want to add is some technical details. So we have two sets of fully transparent glass tubers, concentric. The outer one contains liquid nitrogen that is here to do some pre-cooling and to shield the inner vessel that is filled with helium from radiation and other sources of heating. And so we cool down, we fill the inner dewar, the inner cryostat with the liquid helium, and then we cool it down to the superfluid transition. So our temperatures will be between 1.6 to 2 Kelvin. And what we do, as Leonardo said, we are going to reconstruct the surface waves with this checkerboard that we use as a method to reconstruct the height field. And then we do spectroscopy. So we look for what kind of frequencies we have. So we have a 2+1 system. We look for at the surface. We have time, angle, and radius. So we look at the frequencies in these directions. Before going through the actual data analysis and results, I just want to give some technical details about the design, because it's not trivial to set up a vortex flow in a sealed cryostat at this low temperature. So what we have is an external motor at ambient temperature, which is equipped with magnets that are coupled to the magnets in the disk in number 1 in this plot. And then the disk is, when the motor spins, the coupling is also making the disk spinning, the internal disk spinning, which is spinning the propeller and is creating this vortex that is flowing down the hole and is going back up from going through a flow conditioner, which is this black cylindrical piece of plastic that really looks a simple thing, but is a bespoke 3D printed device that we, through a lot of iteration of the same experiment, designed to decouple the solid body rotation that comes from the propeller. We want to decouple the solid body rotation to the rotation that we want to give to the fluid at the surface, because as Silke and also Leonardo said before, we want a certain velocity profile on the surface. We want a potential velocity profile. I will going back to this later. And also we have the pattern that is, we need it for the checkerboard demodulation, and the experimental zone will be the surface. Okay, so this is a scheme on how we set up this flow. Propeller is spinning, is creating a cavity below the hole. Maybe I should use, below the hole, which is below the flow conditioner, which is this gray L-shaped thing in this scheme. And a cavity means that you also have flow from above, and you have recirculation because it's a sealed system, and recirculation through these small holes that we design in the flow conditioner. And with this system, we figure out that we can actually reproduce two regimes of a vortex. The first one, we call it solid core, and if you look carefully, there is no, it's just a dimple on the surface. It doesn't go all the way down the hole. So how do we explain this? We think that below this dimple, we have a cluster of singly quantized vortices that are, creating this dimple. While if we speed up the propeller At some point, you create a full cavity, a hollow core that goes all the way down the hole. And in this case, you don't have a cluster of singly quantized vortices. You have a single multiply quantized vortex, which is, and this is the kind of quantum to classical transition Silke was talking about previously. Well, let's have a look at a video of the flow again, because you don't see this very often. And just to give you, some idea of the shape and how big is this vortex is. It's actually the biggest vortex with the biggest circulation ever measured. So it's very remarkable. Now, let's jump to the data analysis. So, as Leonardo said, we are reconstructing the surface. And when you reconstruct the surface, you get a signal like this, which is very confusing. So what you do usually, you just look at the modes that are populating your surface. So what you do, you pick a radius, so a fixed radius, wherever you want, and you look at the Fourier spectrum in the time and angle direction. So you look at azimuthal number versus frequency, and you notice that there are some frequencies that are populated, some frequencies are not populated. And in particular, you have these low M modes that are populating every frequency, and these are actually the cause of the weird colors in the previous animation I showed you. So if you filter these modes and you reproduce the animation, then you can see the interesting part. So we figured out in this way that all this vertical line is just mechanical noise due to the shaking of the propeller or the pumps that are also shaking the system, the nitrogen, which is boiling. So, bubbles can hit the inner cryostat and shake it. But, it's easily understandable, and it's a problem that is quite easy to solve. Another feature that is going to be the most important feature of the system is that, as you can see, there are some frequencies that are, for a certain azimuthal number, you have populated frequency above and a certain number, but no frequencies below. And this is actually very important, and I will show you why. Yes. So I just told you that I'm fixing the radius and I'm showing a spectrum, but if you change the radius, the spectrum is also changing, because we also have this dependence in our data set, which is radius, time, and angle. So it's interesting because if you go to low radii, the minimum frequency below which nothing, there is no mode population, is higher for small radii and is lower for big radii. So why? We need a theory for that. We need to find a model and try to see if you can figure out what is going on. And yeah, there is a theory was developed by Sam and Patrick and Silke in 2020, and I don't want to spend a lot of time on this because I want to jump to the results, but I just want to say that we have these two parameters, VR and V theta, which are the two velocities of our surface flow. We have a wave equation. We have a field equation for our system. We have a dispersion relation which is modified by the velocity flow, and we want to figure out what is the minimum frequency that can propagate at a fixed radius at a fixed M mode. And you find it looking at turning points and looking at the minimum frequency of all the turning points you have. So we have we have a lot of free parameters and some other like surface tension, density, and height that are determined by experiment, but we have a lot of free parameters. But what we want to do is we want to see what's the velocity profile of our system, because in the end we want to do analog gravity, so we want to see if it's a potential flow, so we want to see the radial behavior of the velocity, of both velocities, angular and radial. So for every radius, for every m mode, we can calculate the minimum frequency for a different velocity values and find the best match with the experiment. And doing this gives you a very nice prediction of the minimum propagating frequency, and moreover, we also get the velocity profile because we can do it for different radii, and for every radius you get a v theta and vr. And if you plot it as function of the radius, you find out that the radial velocity is practically zero, and Silke mentioned before that there is this Ekman, okay, I only have 3 minutes, 5, better. We have radial velocity is practically zero, so we just focus on the angular velocity, and it's a potential velocity. And moreover, having the potential velocity, you can calculate the number of quanta in your system to have this potential velocity, and it scales with the propeller speed linearly. And we also have a big number of quanta of circulation, so big that it's almost a classical vortex flow. So, yeah, this is the main part of my talk. And this minimum frequency acts as an effective potential in our system, which means why don't we have frequencies below this minimum frequency? Because if you have a mode with a frequency which is smaller of the minimum frequency, the mode is evanescent, so it's not a propagating mode. And you can see it if you plot frequency against radius. You can see we have bound states, and the bound states are these stripes that live between the outer edge of our system, which is just the glass, and the velocity potential, after which the mode becomes evanescent. And if you zoom in and take a slice of some frequency, you can see the absolute value, and you can see that this is looks really like a bound state. Not only this, you can do it for all of them, and you can plot them here and match them with the theory. The theory, I'm not going into the detail, but basically you just take the potential flow, the potential barrier, you take the outer edge, and you fit the bound set that can fit in this region. And if you do it for different frequencies, you find the perfect match with the theory. And this is for co-rotating modes for a specific M mode. And also another thing for this, for example, if you zoom in here and you look at this mode, you can literally see where the bound state is hitting the potential barrier and is becoming exponentially decaying, because it's not a propagating mode anymore after this red point in the radial direction, and so it's decaying. This is why below the minimum frequency you don't have any population, while above you do. And yeah, so bound state for co-rotating modes, and yeah, these two plots refer to solid core and hollow core. In the co-rotating there is not much different, but if you go to counter-rotating modes, so modes that are rotating in the opposite direction with respect to the flow, you see that solid core and hollow core have drastically different features. So in the solid core, you still have a big potential barrier, but it has a peak now. But the peak is very high and it's outside the field of view that we can probe. And so you still have bound states, while in the hollow core, we can see the peak in a region where we still have a high resolution, And what you notice is that you don't have bound states anymore above this potential as expected, and you have a big signal which is zoomed in panel C, which is right on top of our experimental potential. And this is a signature of what we call ringdown modes, which are the aim of the first aim of the project. And so, yeah, of course, this is only a signature. We don't have anything more than this, but it's already remarkable. Yeah, outlook, and then I finish. So what can we do to improve our experiment? Now that we have a working experiment, what can we do more than what we already did? Well, of course, getting rid of the mechanical noise would be nice. It's always nice to get rid of noise. And, well, of course, someone will say, why do you have zero drain? It would be nice to have a non-zero velocity field in the radial direction, because this is connected to black hole horizon and Hawking radiation, which is also a very interesting effect. Detection of light ring modes. So yeah, of course we have a signature of the ring down modes, but we need more than this to be sure that we are detecting them. Understanding the source of the bound states. So you have bound states. What is creating these bound states? Is it the shaking of the cryostat or something else? Also nonlinear theory for the amplitude and growth and decay. So if you can measure the onset of these modes and the decay of these modes. So for example, start the propeller and start recording before starting the propeller, so you see the growth of the modes, or switch off the propeller and look how they decay. And yeah, the last thing is, of course, push it to the quantum regime, where you go down from big values of circulation to small values of circulation, so you can actually see the quantization effect, which we don't see right now. Detect individual quantized vortices, which is below our resolution right now, but Pietro will talk about a new detection scheme that we want to apply to be 1,000 times more precise, hopefully. Yeah, noise-free environment is the dream. Yeah, ultra-precise surface reconstruction. Pietro will talk about it. Thank you very much.